Right, today we're going to be talking about inverses and functions. Yesterday we just talked about how an inverse, we would switch the x and y's. We would switch the x values and the y values, and that would be the inverse. And we didn't really talk about, is the inverse a function or not? Today we're going to take it a step further and remember, determine, is this a function or not? Now remember, a function cannot have any repeated x values. If we have any repeated elements in the domain, because remember, domain is your x values, range is your y values. If we have any repeated values in the domain or x values, then it is not a function. But all of these are relations. A relation is just this value is related to this value over here. But a function is when each x value only has one y value. Y values can be repeated, though. We could have two different x values be related to the same y value, and that is still a function. So let's look at these tables here where we have the original, and then we have the inverse. And we're going to determine, is the inverse a function or is it just a relation? From a table, I want to see, do I have any repeated x values in my inverse? See, -1, +1, 3, 5, 7. None of those are repeated. So that means this inverse is also a function. Then I look at the next one. Do I have any repeated x values? 8, -1, -4, -1, 8. Oh, I have 8 is repeated and -1. So this relation is not a function. It is just a relation. Then here we have 6, +1, +2, 3, +10. None of those are repeated, so this is a function as well. So the inverse of a function is sometimes a function as well. Now, is there a way that we could determine if the inverse is a function without doing this step right here of creating a new table? Can we just use this set of tables or the table of the original function to tell if the inverse will be a function or not? And that answer is yes, we can. Because remember, an inverse is when we switch the x and y's. So if we look at this table right here, we see that we have repeated y values, 8 and 8, and -1 and -1. So we can kind of think further and say, well, if I know that the x and y values switch in an inverse, if I have repeated y's in my original function, that means when I switch them for my inverse, those repeated y values will become repeated x values, making the inverse not a function. So then you wouldn't need to do this step of switching x and y and looking for repeated x values. You could look at the original function and say, oh, we have repeated y values. That means the inverse is not a function. This table right here still represents a function, but the inverse will not be. So how can you look at the table, look at a given table of values and decide if its inverse is a function? If the original function has repeated y values, then the inverse is not a function. So again, be careful of the terminology. It's very easy to get these things mixed up. If we look at the original and there's repeated y values, the inverse is not a function. If we look at the inverse and there are repeated x values, well, then that inverse is not a function. So it depends on what you are given. Are there any questions so far? So let's remember we had something that we could do to tell if a relation or a graph is a function or not, and that was that vertical line test. So a vertical line test, we drew a vertical line, and if that vertical line touched the graph more than once, then that graph itself was not a function. Now we're going to take a step further and say, well, if I have the original graph in front of me, can we determine if the inverse is a function or not? And to do that, I want to look back here. You guys don't need to flip there, but I want to look back at this problem from yesterday, where the green sideways parabola was our inverse, and we can clearly see that this inverse fails the vertical line test. We touched twice. We want to come up with something to say, well, if we didn't have the graph of the inverse, if we just had the graph of this original function, could we tell if the inverse was a function or not? And it turns out there is a way. Instead of a vertical line test, we can do what's called a horizontal line test. And the horizontal line test is, well, a horizontal line. And you see the horizontal line touches more than once. So that means the inverse of this would not be a function. So the vertical line test, and it's going to get confusing. The vertical line test tells you if the graph we're looking at is a function. The horizontal line test tells you if the inverse would be a function. You still look to see if you touch more than once, but depending on what you're being asked to do, you'll do the vertical or horizontal line test. I'm going to go back and leave that. And we verified that yesterday using our table. We saw we had repeated, we had repeated x values in our inverse table, so that means the inverse would not be a function. So how can we look at the graph and decide if its inverse is a function? If we draw a horizontal line and it touches graph more than once, the inverse is not a function. So if we draw a horizontal line and that line touches the graph more than once, that tells us the inverse is not a function. Which brings us to the horizontal line test. The horizontal line test, exactly how it sounds. The inverse of a function is also a function if and only if any horizontal line intersects the graph at once. It doesn't matter if you could draw if you could draw a horizontal line and not touch the graph, up here, you might say, well, I can draw a horizontal line right there, and we touch only once. That doesn't matter because we could draw one up here and touch more than once. So this is a test that we do on the original function to decide if the inverse is a function too. I don't like how that's written. Original and inverse. So here we have two graphs of original functions, and we're going to determine if the inverse is one as well. So yes, we have a horizontal line to help us out. We touch only once. There is no horizontal line that we could draw that would touch more than once. So the inverse is a function because the original passes the horizontal line test. As opposed to this one with the parabola, where we can draw a horizontal line and touch more than once. So that means the inverse is not a function. So let's flip to the next page. So we're going to graph these functions, A, B, and C, and determine if the inverse is a function or not, based on the original graph. So hopefully with letter A, we can all graph this line where your y-intercept is -3 and your slope is -2. So down 2 and right 1, down 2 and right 1. So then your graph would look like that. Well, does this pass the horizontal line test? Yes, it does. There doesn't exist any horizontal line that I could draw that would touch this more than once. So yes, it passes the horizontal line test. So the inverse is a function. Now letter B, our good friend, the absolute value graph. So we need to remember how to graph those. Your vertex is +1, 2. And our A value, the number in front, is an invisible 1. So that means we're going to go up 1 and right 1 from the vertex. And then from the vertex, up 1 and left 1. So there's our absolute value graph. And yes, we can see clearly that if we draw a horizontal line, it is possible to touch the graph twice. So no, the inverse is not a function. It fails the horizontal line test. Now with letter C, you may be looking at that equation saying, I have no idea how to graph that. Well, if you don't know how to graph something, you can always make a table of values. You can plug it in X, get a Y out, and plot that point. So let's do that. Let's plot some points. So our table of values, -2, -1, 0, 1, and 2, we can plug those in to find our y value. So I have my calculator out. -2 to the third power plus 1 is -7. -1 to the third power plus 1 is 0. 0 to the third power plus 1 is 1. 1 to the third power plus 1 is 2. 2 to the third power plus 1 is 9. So we can plot those points. So this graph looks like that. So is the inverse a function? Yes, it is. It passes the horizontal line test. So now let's look at this one down here where we have a quadratic. And you know it's a quadratic because it's 2x squared minus 1. X squared means quadratic. And we could probably tell from up here that a quadratic is going to fail the horizontal line test. So is there a way that we could manipulate this in order for the function to pass the horizontal line test instead of fail it? So let's look down here and graph this. So we'll pick our favorite x values as always. And then we're going to plug those in. So I have my calculator with me. So 2 and then -2 squared minus 1 gives me +7. 2 times -1 squared minus 1 gives me +1. If I plug in 0, I'll get 1. And because it's a quadratic function, we know, sorry, -1. Because this is a quadratic function, we know it's symmetrical. So then these values will be the same. And then we plot our points. So right now, we know we can look at this and say the inverse will not be a function because this will fail the horizontal line test. So no, it fails the horizontal line test. But what if we got rid of some of the graph? So if you look at letter E, what this means right here, x is greater than or equal to 0, that restricts our domain. When we originally talked about quadratic functions, we said the domain will always be -infinity, infinity, or all real numbers. When you see something like this, that tells you that you're changing the domain. We only care about the x values that are bigger than or greater than, greater than or equal to 0. So I'm going to look at my table, and in my table, I don't care about these values. So I'm going to plot 0, -1. 1 comma 1, and 2 comma 7. This is what my graph looks like now. Since I restricted the domain, I got rid of all my negative x values. Now we can look at this and say, oh, yep, this passes the horizontal line test. Because we restricted the domain, the inverse is now a function. So that's why it would be useful sometimes to restrict the domain. So we talked about this yesterday a bit, that the inverse notation has that -1 like as an exponent there. And that's how we can tell that, this is the inverse of f, or the inverse of g. But note that it is not the same as using our properties of exponents. Remember, the property of exponent, we would say, oh, if we have a negative exponent, we can put it in the denominator and make it a positive one, a positive exponent. That's not the case for inverses. So don't think that those are the same. So how do we calculate the inverse algebraically? First, we replace f of x or g of x with y. Then we switch the variables, and that should make sense because when we had a table, we switched the x and y values. So we're going to switch where x and y are, and then we're going to solve for y or get y by itself, and then finally write it in inverse notation. So I'm going to do, we're just going to do letters A, C, and E, and then we'll call it a day. So in letter A, it says y equals 7x minus 4. We already have y. Like we don't have, there's no f of x or g of x to change. We already got that. So we can go right to switching our x and y values. So notice the only thing that I did was I switched where x and y are. The 7 stayed where it is. Now we need to get y by itself. So we'll add 4 to both sides. X plus 4 equals 7y. Then we're going to divide both sides by 7. And when we divide both sides by 7, we get x plus 4 over 7 equals y. So now that we have y by itself, we know we are done, and we can write it in inverse notation. Which again, inverse notation would be inverse, that -1, and that equals x plus 4 over 7. That would be our answer for this one. For letter C, okay, it says f of x. So first we need to change this to say y equals 2 over 3x minus 5. Then we switch where x and y are. We now need to get y by itself, so we're going to add 5 to both sides. So x plus 5 equals 2 over 3y. Now, some of you would multiply by the reciprocal, and I would agree in most instances, I would multiply by the reciprocal or multiply by 3/2 on both sides. But because I have multiple things on the left where that x plus 5 is, I'm just going to multiply by 3 first. These will cancel. And then I had to multiply both of these by 3. So 3x plus 15 equals 2y. And then I'm going to divide everything by 2. And that will leave me with 3x plus 15 over 2 equals y. And now that I have y by itself, I can rewrite this in inverse notation. So the inverse of x equals 3x plus 15 over 2. And that would be my inverse. Any questions before we do letter E? So this says h of x. First thing we need to do, change it to y. Okay, so I change that to y. Then we need to switch where x and y are. Subtract 9 from both sides. Oops, I forgot to make this a y. Okay, so I've subtracted 9 from both sides. Then I'm going to multiply both sides by 4. When I multiply both sides by 4, these go away, and I'm left with 4x minus 36 equals negative 3y. So then we need to divide everything by negative 3. When I do that, I'll get negative 4x over 3, but negative 36 divided by negative 3 is positive 12. Now that y is by itself, I can then go back and replace it with the inverse notation. And we started with h of x. So we would say the inverse of h of x is negative 4x over 3 plus 12.